All right, so tonight's topic, we're going to move on to characters. So we've talked about encoding numbers, integers, floating point numbers, BCDs. So now let's talk about characters, how characters are encoded. So characters are the not necessarily numeric, but values like your alphabet, like A, B, C, D, and hashtag, and even numbers, but not numbers in the term of numeric numbers, but even numbers encoded in a character. Okay, so let's start off with the lowest common denominator for characters, ASCII. Everyone here has probably heard the term ASCII before. So ASCII stands for American Standard Code for Information Interchange. So this is based on the English alphabet and was actually developed before the computer, so at least the modern computer. So this was originally developed for telegraph and teleprinters. So if you ever seen really old movies back in the day, where you have a telegraph, where usually train robberies, and someone's will like send a message that says hi, how are you, stop, next line. So essentially they're typing in one spot and then relaying the message to somewhere else where it gets printed out. So because this was developed before the computers were organized as memory into bytes, right? I think we talked about that. So one byte has 8 bits. So ASCII doesn't actually take up 8 bits, it's 7 bits. So because it's just enough to represent all the characters in the English alphabet and plus some control characters. So the ASCII standard is 128 characters and it's stored in 7 bits. So these 128 characters is composed of letters like the alphabet, right? A, B, C, D, numbers like 1, 2, 3, and then also control characters. Control characters are things that aren't not necessarily printed out, but they're for the purposes of printing. Like for example, it could be line feed or tab. These are control characters that move the cursor around. So because things are moved or stored in 7 bits, computers nowadays store things in 8 bits. So what happens is that on every single byte, there's 1 bit that's unused. And as we have covered before in the past, is that computer scientists are clever guys. They don't like wasting space. So they're trying to always maximize the use of space whenever possible. So someone looked at it and said, well, we're using 7 bits and this 8th bit is unused. Let's use it. So the 8th bit was used by computer vendors to extend ASCII by adding their own characters. So this worked out well for expanding the character set to 256 characters, right? Once you add 1 extra bit, it doubles the number of characters representable. So now you have 256 characters and all was happy, except when you have equipment from different vendors. Then you're going to have issues because that 8th bit is implemented differently because it's not really a standard. It's implemented by each vendor. So each vendor will have their own encoding. So this worked out well if you lived in a world where everything was made by IBM. If you happen to have IBM equipment and AT&T equipment, then you might have a problem. So there needs to be a better way. So before we go to the better way, let's take a look at the ASCII table. So the ASCII, here is an example of the 128 ASCII characters. So this is organized in 3 columns. We have decimal, the hex value, and the actual character itself. So this is a representation of it. If you look at the character column, it's in green. Notice that everything from 0 to 32 is encased within brackets. So these are just control characters. If you look at the character decimal 32, it's space. So it's not really printing anything. It just adds an empty space, right? So it's not until character 33, decimal 33, that you have the printable characters. So with 33, you have the exclamation point. 34, you have the asterisk. 35, you have the hashtag. And let's go all the way up to decimal 65. That's where you have big letter A. And then you have 97, which little a. So this is not to be confused with fonts. Sometimes people confuse fonts with characters, and I can understand the confusion. But in this case, there's no font, there's no stylization. It's just the representation of big letter A, capital A, and lowercase a are actually 2 distinct characters, okay? So the representation of the characters is ultimately when stored in your computer, it's going to be zeros and ones. But in this particular table, we have the number bases for decimal and hex. So these are two different representations of that character. However, once it's stored in the computer, it's going to be 0 through 127 in binary. All right. So now let's talk about what happens when we have more than 128 characters, because this is great if we're only dealing with English, but what happens when we move on to the closest language to English, which is Spanish? You have, its alphabet has one extra letter, and it's a letter N with this squiggly thing over it. It's Enye, right? So there's no representation of that in ASCII. So to solve this problem, the successor to ASCII is Unicode. So Unicode assigns a number, or what's called a code point, to each character. The Unicode standard supports 1,114,112 distinct code points. So to keep things simple, let's just say it supports 1 million. Okay, it supports 1 million code points, and the code points are in hex from 0 to 10FFFF. However, even though it supports up to 1 million code points, the current version of Unicode standard only defines or contains 110,000 characters. So you might wonder, well, if the standard supports over 1 million code points, how come only 110,000 are defined? And that's because 110,000 characters is currently enough to represent every character in every language in the world. So that's roughly only 10% of the number that Unicode can support. So we still have 90% to go in case new languages are developed, new characters added, plenty of room for growth. Now for backward compatibility, the first 128 code points are the same as ASCII. So for example, we said that the letter 41 was big letter A, right? Hex number 41 is big A. So is ASCII. All right. So again, this is just backward compatibility. So another thing about code points is because you're dealing with a large number, up to 110,000 different characters, the standard for writing a Unicode code point is U plus, and then the hexadecimal number of the character, right? So very important is that when you write or reference a hexadecimal value, it's written as U plus, and then the hex value, all right? So look at the difference. This is 41. If we go to ASCII, notice that hex 41 is over here, but it's decimal 65. All right, so when you're encoding Unicode, make sure that you are encoding the hex value and not the decimal value. All right, so now that we have a general understanding that Unicode assigns a hex value to a character, ultimately, when it gets stored back into a computer, it needs to be in binary, zeros and ones. So how do we do that? So like many other things we cover, there's more than one way to do it. So Unicode encoding, there's actually several different formats. So UCS2 is one of the early formats, and it used 2 bytes, and it's now obsolete. The reason it's obsolete is because it can't encode every character in the current Unicode standard. Because remember earlier I mentioned that the current standard has 110,000 characters. So let's just do a little mental exercise. If something uses 2 bytes, and each byte has 8 bits, so 2 bytes with 16 bits. So this is roughly 64,000. So 64,000 is not going to be enough to encode 110,000. All right, so that's why UCS2 is no longer used, because it can't encode every character. So the current 2 standards that you see these days is going to be UTF-8 and UTF-16. UTF-8 is a variable length encoding that uses 1 to 6 bytes, and it's used by Unix and HTML. UTF-16 is a competing standard that uses 2 bytes or 4 bytes, and just by looking at where it's used, you can see it's predominantly used by one company. All right. So for tonight, we're going to focus on the actual encoding. We're going to look at UTF-8. So UTF-8, as I mentioned earlier, is a variable width encoding. Variable width means that it's not always the same size. So it can be 1 byte or it can be 6 bytes, depending on what you are encoding. And just as before, we mentioned with Unicode, the first 128 characters are going to be the same value as ASCII for backward compatibility. All right, so very quickly is that how do I know that UTF-8 is used on a particular document? Well, one way you can do to find out is look at the HTML or the source of an HTML document. You might have a tag that reads meta character set, and this is where you see UTF-8. Okay, so this is just an example of where you might see this. All right, so now let's jump in and take a look at the specs on UTF-8 and how to encode a code point into zeros and ones. So let's take a look at this table. It's a lot to take in at the beginning, so don't worry. Again, we're going to go through this. So when you encode a character into UTF-8, the first thing you need to do is determine how many bytes are needed to encode this character. Okay, so how do I know how many bytes are needed? Well, you don't need to memorize this because you will be able to use this table. So this table shows you that if a number or code point is within this range from 0 to 7F, it uses 1 byte. If the hex value is between 80 to 7FF, it's going to use 2 bytes. So now let's take a segue into hex and counting up hex values. So with hex values, let's contrast that with decimal to make sure everyone's clear. So if I did a number sequence in decimal, you have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the next number would be 10, right? 11, 12, 13, 14, 15, 16, 17, 18, 19. And then we have 20, 21, all the way down to 29. Okay, so why is it called decimal? This is a review. It's called decimal because there are 10 distinct digits here, right? So that's why it's called decimal. Now for hex, you have 16 values. So the values are 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And after 9, you have A, B, C, D, E, F. So what's a value after F? Or what's a number after F? It would be 1, 0, 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, 1, 6, 1, 7, 1, 8, 1, 9. And then after 1, 9, it's 1A, 1B, 1C, 1D, 1E, and 1F. So what's after 1F? It goes to 2, 0, 2, 1, and then all the way down to 2F. Okay, so the reason it's called hex is because each one of these columns has 16 values. All right, does everyone see that? So when I have a number, like let's just say 85, 85 would be larger than 80, right? Oh, I'm just going to write it this way so it's easier to see. It's greater than 80, but it's less than, let's just say 7FF, right? Because you pad this with a 0 and you notice that this is this will be the largest number. Okay, so that's what we're doing with the ranges. So let's look now with this understanding, let's look at this range. So if we look at this range over here, that I'm going to highlight again in yellow, 80 to 7FF, it means that if a number is between that range, right? So it could be anything from 81, 82, 83, all the way up to 7, F, E, right? Would be so anything in between will fall in that range. So the key when you get a code point is to figure out which range does it fit. There's only going to be one of 6 ranges. Where's the number fit? And once you do that, you know exactly how many bytes there are. And once you know how many bytes there are, then it comes the fun part where you get to fit it into this template or these templates. So every UTF-8 falls into a template of leading and continuation bytes. So let's just start off with 1 byte. This is like a base case. If it's single byte, then the template for filling in the byte would be, if you look at this, it would be 0 followed by 8 bits. So over here, they put X's here, right? So X just means could be 0 or 1. So this is a template for 1 byte. So if you have 0, it begins with 0, and the remaining 7 bits is going to be the binary for whatever you're trying to encode. Now let's take a look at 2 or more bytes. If you have 2 or more bytes, I want you to look at a pattern here. Look at the continuation bytes. Notice that all of these continuation bytes all begin with 1, 0. Does everyone see that? So all continuation bytes begin with 1, 0, and the remaining 6 bits are used to encode your value. Now let's take a look at your leading byte and see if you can see a pattern here. So for the leading byte, I'll give you a hint. Look at the number of 1s in the leading byte and figure out its relationship to the number of bytes in the character. Do you see the pattern? So the number of 1s you see in the leading byte tells you how many bytes there are inside this character. So let's take a look at some examples here. The first one here, 1, 1, 0. There's 2 1s here. So it knows that, so that means that there's 2 bytes in this character. Let's look at this one down here. If we count the number of 1s inside that leading byte, it's 5 of them. So that means that there are 5 bytes in this character. Okay? So every character, once you determine how many characters there are, the next step is to write out this template for your byte pattern. And then we fill it in. All right, so let's quickly go through an exercise just so you can see how this is done. So first, let's do a really easy one. The first easy one is the $sign. The $sign is Unicode 0.24. So let me come up here. And I want you to look through here and say, okay, if the code point is 24, is 24 larger than 0? It is, right? And is 24 less than 7F? It is. So 24 is between 0 and 7F, so that means it takes exactly 1 byte. So because it takes 1 byte, I know that it's going to look like this. It'll be 0 followed by 1, 2, 3, 4, 5, 6, 7. 7 bits. Okay, so now I need to fill that in. So how do I do that? So the next step is I need to convert, this is currently hex base 16. I need to convert this to binary. So as a quick review, do you remember, how do I convert hex to binary? Groups of how many? Groups of how many bits?
4.
Is it 3 or 4? 4, exactly. So what you do here is say 4 is 0, 1, 0, 0. And 2 would be 0, 0, 1, 0. Okay, and this is the binary. And what you do here is you start with the least significant bit, 0, and you put it over here. So you start from the right, and I'll write in 0, 0, 1, 0, 0, 1, 0. And that's my answer. And that's how you encoded the $ into UTF-8. Okay? All right, let's do one more example. The next one is going to be a little harder. So we did dollars. Now let's do cents. So cents, its code point is A2. So with A2, let's take a look at how many bytes you're going to need. So let's start with, if A2, we know it's larger than 00. Okay, so that means this is checked. But is it less than 7F? Is A2 larger than 7F? Is A larger than 7? It is, right? So you know that it's not going to be the first row. So it's not in this range. So let's look at this second row. The second row is 80. So A2 is larger than 80. And is it less than 7FF? A2 is less than 7FF, right? Because A2, you pad it with a 0 in front. Yeah, it's less than 7FF. So that tells you that it's going to be the second row. So it takes 2 bytes. Now, because it takes 2 bytes, then we know that's going to follow this pattern. So let me open up the whiteboard. So we have A2. We know that it takes 2 bytes. So because there's 2 bytes, the leading byte is going to look like this, 110, to show that there's 2 bytes. And then I have 5 more bits for my value. And then the trailing byte or continuation byte will be 10, because they always follow the format of 10, and then 6 bits. Okay, so it's going to follow that template. So what I need to do now is take A2 and convert it into binary, right? So this is going to be 0010, and A is going to be 1010. Once I have that, I want to start from the least significant bit and start populating that. So this will be 0, 1, 0, 0. And now I'm going to take this guy and populate over here. Again, from the right, it's going to be 0, 1, and then 0, 1. Okay, and then fill out the rest. We'll pad it with the zeros. So I'm filling it out from right to left and filling in the blanks. And this is your UTF-8 for the symbol, the cent character. Okay, so this is code point A2. All right, any questions so far? All right, so give you guys something to do. Now that you have a general idea of how to do it, I want you guys to encode this code point. U plus 10012. Okay, so let me copy this and put it on the whiteboard. And let me also copy the table here so you can reference it. All right, your first step is determine how many bytes there are going to be needed. And second, convert it into binary and then fill in the bytes. All right, so give you a few minutes to work on this.
Professor, I have a question. Professor.
Go ahead.
what would you call this U plus 10012? Is that just like a hexadecimal number, or is it
It's a hex, yeah, it's a hex value.
but it's like a Unicode UTF?
It's a Unicode Unicode 0.10012, and I don't know the character off the top of my head. It's gonna, because it supports currently 110,000 characters defined. So this might be one of those weird characters you've never seen in a foreign language.
All right, so it's just a hex value. All right, thank you.
Yeah. Okay, so let's do this together. So code point 10012 looks like it's going to fall between here and here, right? So this is going to take 4 bytes. So the bit pattern is going to be 1, 2, 3, 4. So 4 bytes, and that would give me 3 left here. And then 1, 0, 1, 2, 3, 4, 5, 6. 1, 0, 1, 2, 3, 4, 5, 6. And then 1, 0, 1, 2, 3, 4, 5, 6. Okay, so plugging this in, this would be converting, would be 0. Oops, I actually will need more space in that, so let me move this over a little bit. This will be 0, 1, 0, 0, so that's 2. This is 1. I got 2 zeros and a 1. Okay, so again, starting from the right, I move that over. This will be 0, 1, 0, 0. I'm just going to highlight this with yellow so you can see that's where this came from. And I'll just use a different color. Let's do green. And this guy would be the next one. This would be 1, 0, 0, 0. And I'm going to highlight that with green to show that that's where it came from. And then let's do the next color. Let's do orange. So this 0 would be over here would be 0, 0, 0, 0. Okay. And then let's do another one. Let's do pink. This would be 0, 0, 0, 0. And the last one, let's do blue. And this would be 1, 0, 0, 0. I can just pad it with a 0 now. Okay, and this is this blue one. All right. So essentially, I'm taking everything from the lowest to the highest, and I'm just filling in the spots that I had, for populating my value. All right, and that's your answer of how this code point would be encoded in UTF-8. All right, did everyone get this? Okay, It's a little quiet. All right, so let you guys work on one more exercises. All right, so let's do a slightly different one. Let's do U plus A1A. Okay, and I'm going to copy the chart over again. All right, so have at it. Give you a few minutes to do this. Again, figure out how many bytes there are, and then write out the pattern for the byte, and then fill it in. Okay, so let's do this together. All right, A1A. Again, this is just helping with hex, right? So A1A would be larger than 800. Let me change the ink here so you can see the color more easily. So A1A is larger than 800, but it's less than FFF. So we know that's going to be 3 bytes. So the bit pattern for the 3 bytes is going to be 1, 2, 3, 3 ones and a 0, and then we have 4 spaces left. And then I have my 2 continuation bytes to reflect that this total should be 3 bytes. Okay, so this is a pattern that needs to be filled in. So now we convert this to binary. A is 1010, 1 is 0001, and A is 1010. So start filling it in from the right. You would have 0, 1, 0, 1, and then the next number is 1000, and then 0101, and then we just pad it with zeros. And there you go. And that is going to be your encoding, UTF-8 encoding for code point A1A. All right. So are you guys starting to get the hang of this?
Yes. Is this the only type of sort of encoding type that we'll have to know for the midterm? Will we need to know like UTF-8?
We know UTF-8, correct. So know it very well, because that way, enable you to encode a character into binary and from binary back to a character.
So UTF-16, we don't need to know.
No, just UTF-8. As long as you have understanding one encoding, I don't need you to memorize. There's more than 2 encodings. So I just needed you to be very familiar with one of them, just so you know how you go from zeros, and ones to a character. That's what I'm primarily concerned with, that you understand that characters are not encoded as ABC inside your computer, but they're encoded as zeros and ones, and at least you know one way of how to convert the zeros and ones and how it represents a character. Okay?
Cool. Thank you.
Yeah. All right, so let's do a couple more exercises. I'm convinced you guys know how to do this. All right, so one last one for is we'll convert this ABC123 and convert it into UTF-8 encoding for zeros and ones. Okay, so let's work on this exercise. So given this hex value, I want you to encode this character into UTF-8. All right, so I'll give you a few minutes. Okay, so let's quickly do this now. So looking at this hex value, ABC123, it's larger than 2000, but it's less than 3FFFF, right? So this is going to take 5 characters or 5 bytes. So the bit pattern for the 5 bytes is 1, 2, 3, 4, 5. Okay, and then it's 1, 0, 1, 0, 1, 0, 1, 0. Okay, so these are going to be my 5 bytes. And now I just want to convert this to binary. So 3 would be 0, 0, 1, 1. 2 is 0, 0, 1, 0. 1 is 0, 0, 0, 1. C is 1, 1, 0, 0. B is 1, 0, 1, 1. And A is 1, 0, 1, 0. Okay, so I need to put this guy over here, starting from the right, start filling in. So this would be, well, I'll use a different color ink. How about that? This will be clear. 1, 1, 0, 0. And then 0, 1, 0, 0. And then 1, 0, 0, 0. And then 0, 0, 1, 1. 1, 1, 0, 1. And then 0, 1, 0, 1. And then pad it with zeros. Okay, and there you go. This is the UTF-8 encoding for the hex value ABC123. All right, so as I mentioned earlier, we want you to be able to not just convert a hex value to UTF-8 encoded zeros and ones, but what if you are now given data in the other direction? What if you are given these values and you're presented with these bytes and you're asked what characters are encoded here, right? So that's what we'll do. So let's open this up. All right, so there's 2 characters here, right? The first one, if we look at it, this tells me that there's 2 bytes here. So I highlight the template for the bytes, right? And this is part of the template. So what's left is I want the values in blue. Those are my values. Okay? So once you have that, I'll give you a few minutes. I want you to extract these values in blue and then do groups of 4. We're working backwards now. You group them into groups of 4 and convert them to hex. And tell me which 2 code points are encoded here in this. All right, give me a few minutes. Okay, so now let's take a look. Let's break this apart. Extracting the values from this template, you from the first code, it's have 1 1 0 0. Excuse me. 1 1 0 0 0 1 0 1 0 0 1, right? 1 1 0 0, 3 zeros and a 1, and then 0 1, 2 zeros and 1. Okay, so here I'm going to break it into groups of 4, right? And then the last one I can just pad with a 0. So this is, first is 3, this is A, and this is 4. So this is code point 4A3. The next one is 1 0 0 1 0 0, and then have 0 1 0 1 0 1, and then 1 0 1 0. Okay, so now I'm gonna groups of 4, and this would be 9. This is 8. This is A, and this is 5. Okay, there you go. So again, just remember groups of 4. So this time working backwards, you create groups of 4 and then convert them to hex, and there you have it. All right. Hopefully, if you get any questions or on the exam or on any exercises, refer to this table when necessary to determine how many bytes there are. But once you have that, the key thing here for these exercises is really converting from hex to binary. Okay. All right, so let's move on. Next topic, compression. So compression is encoding information using fewer bits than the original representation, right? So popular forms of compression, everyone here might have already used zip, like WinZip, or compress folder. So these are all concepts of just re-encoding information. So it's not UTF-8, it's not ASCII, it's creating new encoding for your text, or it could be numbers, or whatever, but information is being re-encoded using fewer bits than the original file. So there's two main types of compression. You have lossless data compression and lossy data compression. So lossless data compression means that I am able to reconstruct and recreate the original data with no loss of information. So this is primarily what zip is. Like when you zip a file, like your term paper perhaps, or your program, you want to be able to uncompress it and extract it with no loss of information, right? So that makes the most sense to people. So why would you, if you can do it without losing information, why would someone want to use lossy data compression? So lossy means that you are allowing for some loss of information, and with the reconstructed data is not the original, it's an approximation, some detail was lost. So why would anyone want to use lossy data compression? And the reason is, with lossy data compression, you can be more aggressive, which means that files can be shrunken and compressed more, as long as you lose some information, and it's fine. So examples of lossy data compression tends to be large files where you wouldn't notice things that are different. I'll give you an example, is pictures. You have your latest iPhone, you take a picture that's 14 megapixels, right? So 14 megapixels means 14 million pixels. So your file size, arguably, you might think, oh, it should be 14 megabytes per image. But you notice that when it saves to your phone, the image is only a JPEG and it's only 2 megabytes. So what happened is that the 14 megapixel was taken, but the actual picture that was saved, even though it has all these pixels, the colors might have been reduced, right? Or the resolution might have been changed. So these are two common ways of reducing the size of an image file. The most common way tends to be lowering the resolution. Instead of 1 million lines by 4 million lines, they'll say, okay, let's make it 500,000, 500,000 by 2 million. So basically reducing the number of lines, thinking that if you're looking at something on a phone, you're not going to see 14 million lines anyways, so you wouldn't notice a difference, right? Other times it will be on web pages where you might have very high resolution image, but they figure, well, we need speed, we need to be able to load an image very quickly. So you might notice that the image size isn't as big. Other ways of reducing losing losing information is colors. Is that instead of having 16 million distinct colors on this image, it might have been reduced to 64,000 colors, with the idea that most people would not notice it when they stare at your phone. Okay, so that's what a lot of C data compression mostly is that they're changing some information and deliberately reducing the amount of information that's being encoded. So now let's take a look at one of the underlying mechanisms that allow for compression, right? When you compress a file, it's not really squeezing your file, even though the visual image is that you take a file and you squeeze it and squeeze it and squeeze it, it's smaller. Well, that's a nice, mental picture of what happens, but that's not actually how it works. So data compression, there's a lot of different algorithms for it, but the main principle behind compression really is finding patterns of redundancy and repetition. So if you have data that is repeated multiple times, then that's something that can be re-encoded using fewer bits. So I'll give you an example of what I mean. Let's just say that I have a big picture, right, of the American flag. It has a lot of pixels in it. So let's say for the next 1,000 pixels, they're all the color red. So I can record the number red or value red for 1,000 instances of red, 1,000 times, right? And have 1,000 pieces of information that says red. Or a clever way of doing it is say, oh, the next 1,000 things are red. So I just need to encode the value red and then record a number next to it, says 1,000. So it knows that the next 1,000 values are red. So now instead of having 1,000 pieces of information, it's only 2 points of information, one with the color and the second point with how many, right? So that's just one example of doing that. But that's only made possible because I had repetition, right? So again, I can't go over every possible algorithm for compression. So I'm just going to go over one of them, just so you have a general idea of how it works. All right, because they all operate more or less on the same principles. All right, Huffman encoding. So Huffman encoding is a very early and popular way of encoding text, or it could be numbers, but using less characters than needed. So Huffman encoding employs a variable length encoding for your characters. So it's based on the frequency of characters. It finds characters that are used the most often, and it represents it using the smallest binary numbers. And for the least often used characters, it uses the largest binary numbers to represent it. So what does that mean? Well, what that means is that on any given text document, A, E, I, O, U, the vowels happen a lot more often than the letters X, Y, Z. So if we were just using ASCII, every single character would use 7 bits, right? So with Huffman encoding, they said, no, don't do that, because certain things happen more often than others. So that, like the vowels A, E, I, O, U, you want to use a variable length encoding that has a smaller number of digits to represent things that happen the most often. So your file will end up being smaller. Okay, so let's just see an example of how this works. So let's start off with the magic word, abracadabra. Abracadabra is composed of the letters A, B, R, C, D. There's 11 of them in that word abracadabra, 5 distinct characters. So in our example here, let's say we're not using ASCII and we try to be optimal and say, all right, what's the minimum number of digits binary digits I would need to encode these 5 characters? And if we look at this example here, is that you would need 3 bits to encode 5 distinct characters. So in this case, A would be 000, B would be encoded as 001, R would be 010, and then we finish with D as 100. All right, so every one of these 5 characters has a unique 3-bit representation. So if each character is 3 bits and abracadabra has 11 characters, then you would need 33 bits to store the word abracadabra. Okay, does everyone agree with me here? So if abracadabra has 11 characters and each character is 3 bits, it's 11 times 3, you have 33 bits that are needed. Okay, so keep that number 33 in the back of your head. Now let's go through Huffman encoding. So now what Huffman is going to do is lists out all the characters in the word abracadabra, and it breaks out the frequency of each character. It sees that A happens 5 times, B happens twice, R happens twice, and C and D only happen once. So now it has this frequency. Then it goes and builds a table. So right now, I want to be very clear, you are not responsible for building this table. This is really going to be a binary tree that you will cover in data structures. So you're not responsible for knowing how to build this. This is just for illustration purposes, just so you can have an idea of how a Huffman encoding works. So in this case, looking at my table on the left, we see C and D are 1 and 1, happens once. So it gets placed at the bottom node. So C and D, and then it takes the next value is R, is placed up there, and it keeps moving up this table or this tree, right? So you have B is next, and then very last is A is all the way at the top. So the things that happen the least often are placed at the bottom, and the things that happen the most often are placed at the top. So what's the whole purpose of creating this tree? So this tree is created so we can generate a code. So for example, if we want the letter A, it just goes from the top to A, and notice it's 0, and that's where we have A equals 0. Now to get B, we start from the top, it goes 1, 0, gets to B. So B is 1, 0. So notice that by doing this, I'll do it for each letter. Let's say to get to D, it would be 1, 1, 1, 1 to get to D. And that's why D is 1, 1, 1. So after this is done, notice that my new encoding here, A and B happens the most often. And notice that it only takes a single bit, 0, to represent A. B happens the next most often, and it's only 2 bits, 1, 0. So they're both less than 3 bits. But if you were an astute observer, you might say, but wait a second, Professor Jackson, look at C and D. C and D are 4 bits. They're larger than 3. Using my fixed width earlier, there everything was 3 bits. But here, C and D is 4 bits, right? On average, it's 4. I mean, it's 3, so it should even out, right? And the answer is no. Because remember, C and D only happen once. A, B, and R happen more often. So if we take that and we now encode abracadabra using this coding, A is now 0, right? So let's take a look at this. A is 0. So I put zeros for A's. B is 1, 0. So I put 1, 0 for all the B's, right? And I'll do it for all the rest of them. Once you put all those in, count up the bits that you had. And you're going to see that using Huffman, you only needed 23 bits to encode abracadabra versus the 33 bits we needed earlier using a fixed width. Okay? So that's pretty much how Huffman works, is that the reason it's smaller is because it's finding the most often used characters and using the smallest number of bits to encode the most frequent characters. And the ones that are less frequent, it uses the longer ones. So on average, your file will be smaller. Does this make sense to everybody?
Yes.
Okay, fantastic. All right, so one key thing about any encoding is that once it gets encoded, right, if we save this to a file, this value, how do we know it's abracadabra? Because it's no longer ASCII, it's no longer Unicode. It's using this table that was created that needs to decode it. So as part of every zip file or any kind of file you compress the file, it has to have some kind of key to decode itself, right? Because if you just look at the file by itself, you can't really decode it because it's no longer encoded using a standard. So with that being said, let's go through our last exercise of the night. Okay, so I have this file here. I'm gonna delete these two that I did earlier. Okay,
So I have this Word document. Let's look at the properties of this file. It's 215,000 bytes, right? So I'm going to send to compressed folder. I'm going to zip the file. Okay, so this is not a document that I created. Let's take a look at it. Everyone looks at it and say, well, look at the size. It's 165,252. So it's smaller than 212. So 215. So we know that this is now smaller. That's to be expected, right? So now comes a question. What if I compress this again? It's already been compressed, but what happens if I compress it again? Is the small file going to get smaller? Is it going to be the same? Or is it going to be larger? What do you think it's going to happen?
Same.
You think it's going to be the same? All right, let's take a look. Compare this 165,252, and once it compress it again, it's 165. What is it? 382. It actually got larger. So do we know what happened? Is that after it was zipped the first time, it took a file and then it optimized it, re-encoded it using the most frequent, whatever algorithm was using. Also, all the repetition was taken out as much as it could. So when you compress it again, there's not much for it to compress anymore. But why is the file bigger? It's because it's re-encoding the newer zip file. So now you've part of that overhead, whatever table or the decryption key or whatever is in there is that little slight overhead metadata that's part of it. So it added about 100 bytes onto the size of your file. Okay, so if I compress it again, do you think it'll get larger? Once it's compressed, yeah, it's going to get larger slightly. Okay, all right, so that's pretty much it, guys.
This